All right, guys. In this video, I'm just going to be going over the FCPS chemistry summative review packet that you got. So if understand what this is. So like kind of like how in biology you had to take a test like once every quarter or so. That was like a standardized test that all Fairfax County student biology students took. They're kind of trying to do that the same thing with chemistry, and this is the first year. Um, and so all the chemistry students in the county are going to be taking this, and we're going to have one. It's not going to be every quarter, but we're going to have one periodically throughout the year. And this is the first one. And so we're taking the first one the day before break. It's pretty short. It's only 26 questions, and it shouldn't take that long, probably a half an hour max. Um, and just understand that it's called the chemistry summative through the county, but it's only going to be a formative grade for us. And the way to think about it is it's kind of like a practice SOL, but it will only cover the content we've covered so far. So basically, this is kind of like a midterm type deal. It has content on it, questions on it that cover stuff that we have covered so far in chemistry. So our units 1, 2, and 3 is the stuff that you'll see on this test. But again, it's only 26 questions, and it doesn't cover everything. There's um, there's certain questions, but everything that's on it we have discussed in chemistry so far this year. So nothing to stress over. We'd like you to do your best. The county is just collecting data, and it's mainly for the students that are taking the chemistry SOL in May. None of my students this year in honors chemistry have to take the chemistry SOL. But again, the county wants the data, so we're all going to take it. It's only going to be a formative grade. We'd like you to do the best you can, but understand it's not that big of a deal. Do your best, and maybe you'll get like a candy bar or something if you get a perfect score. It's not that difficult, and if you do the review and you understand everything that's on the review packet, you should be in great shape. Okay. In the format of the test, it's going to be electronic. You'll get a paper periodic table to reference, but you'll be taking it through a Schoology assessment. Okay. So if you look at this review folder, you have the checklist for the assessment with review problems. You have the answer key to the review problems if you want to check yourself. But you also, again, you don't have to do this, but this Schoology assessment, if you do the review problems and you want to check your answers, you can input those answers into this Schoology assessment, and it'll check your answers for you. Okay. So let's just look at the checklist first of all. So again, kind of think of it as like a midterm up into this point. So our units 1 through 3. And on the checklist, I put kind of what our VLO is covered. So here it says 2-5. So when did we learn this? In 2-5. Like when did we learn this? In 3-1. So you can see most of the stuff comes from unit 2 and 3. And really the only unit 1 stuff that's covered on this Fairfax County assessment is 1-4, and it's really just mole calculations, moles to particles or particles to moles, that kind of thing. So there's not a lot of stuff from unit 1, so there's no like percent error on this. There's no you'll need to know significant figures, but that's just throughout the year. But like the safety stuff isn't on here. The lab equipment stuff isn't on here from unit 1. There might be some metric system stuff, but not really. It's mainly the mole calculations, and there's only like a couple of them on here. Okay. So on this review packet, you have review problems. And so for the rest of the video, I'm just going to go over how to do these review problems. And if you understand that, you should be in really good shape. Okay. So let's look at the answer key. Okay. So this one, number one, we're given moles of a compound, sodium chloride, and it's asking for formula units. Remember, if you get confused with what a formula unit is, it's kind of like the word molecule, but it's for ionic compounds, and molecule is for covalent compounds. Uh, if it helps, just change it to the word particle. So it's how many particles of this compound, or sorry, how many moles of this compound are in this many particles. And so remember, to go from particles to moles, you just divide by Avogadro's number. So all we have to do is the number of particles divided by Avogadro's number, and that'll give us the moles of the compound in this case. And we had 3 sig figs here, 3 sig figs for Avogadro's number, so we should round to 3 sig figs for our final answer. Okay. And then this is just kind of the opposite. Here it's how many water molecules are found in a 2.6 mole sample of water. Now, the word for a particle of water is a molecule because water is a covalent compound, unlike sodium chloride, where the word for particle for an ionic compound is formula unit. But regardless, if to go from particles to moles, we divide by Avogadro's number, then to go from moles to particles, we multiply by Avogadro's number. So all we have to do is take the 2.6, multiply it by Avogadro's number, moles will cancel out, and that'll give us molecules of water. And that's all we have to do. Now, for this one, since our mole number only had 2 significant digits, we should round our particle number to 2 significant digits. Okay. For number 3, dot structures. Remember, you just got to know how many valence electrons the element has, and that's how many dots you draw. So we should know that carbon has 4 because it's in 4A, phosphorus has 5, chlorine, all the halogens have 7, the noble gases have 8 except for helium, which only has 2, and then barium is an alkaline earth metal, so that's the second group, and so that has 2 valence electrons. So remember, don't pair up the electrons until you have to. You write the chemical symbol, pretend it has 4 sides. And so for carbon, you're not going to have any paired electrons because it's just going to be 1, 2, 3, 4. So this would be the dot structure for carbon. For phosphorus, phosphorus has 5, so you are going to have a pair of electrons. And it really doesn't matter where you write that pair. You could put the pair over here, the pair over here, the pair over here. It really doesn't matter. But usually when it's 5 dots, usually that's kind of how it's written, chemical symbol with 2 on top and then 3 on the other sides. Okay. So for a halogen with 7 valence electrons, you're going to have 3 pairs of electrons and then 1 unpaired. Okay. But again, you could have like 2 here, 2 here, 2 here, and then 1 here, or you could have 2, 2, 2, and then 1 on top. It really doesn't matter. But here is a halogen. For a noble gas with 8, you got 4 pairs. For helium, technically, this is the better way to draw helium, because helium's valence shell is energy level 1, and energy level 1 can only has 1 orbital, the 1s orbital. And so technically helium's electrons are paired. It's so drawing them this way is better, but if you drew it this way, that's fine. But just remember, helium only has 2 valence electrons. It has 2 total electrons, and they're considered valence electrons. But for barium, it has 2 valence electrons, but don't pair them up. Okay. All right. So here it says, given the electron configuration, identify the element and then predict what charge it becomes when it becomes an ion. So we should be able to look at this electron configuration. It ends in 4s2. We should be able to find 4s2 on the periodic table, and that's calcium. Okay, so the element's calcium. And then it's a metal, so we should understand that it's going to lose electrons to become an ion. When metals lose electrons, they lose their valence electrons. So here are the valence electrons. Calcium is going to lose 2 electrons, so its charge is going to be +2. Okay. The trend for atomic radius going across the periodic table. Remember the snowman. A snowman gets bigger as you go down, but if you tip the snowman over, it's going to get smaller going across. So going left to right across a row, atomic radius decreases. So for electronegativity, remember it increases going up and to the right. Fluorine is the most electronegative. Oxygen is the second most. So of this grouping of elements, oxygen is going to have the highest electronegativity, and phosphorus is going to have the lowest. And this is the order in between. Okay. So just remember, group one is the alkali metals. So the metals in the vertical column, group one, are the alkali metals. Remember, hydrogen's not a metal, so don't include hydrogen in this. The halogens are the second to last group on the periodic table, so fluorine all the way down. The noble gases are the last group on the periodic table, so He all the way to Og. The alkaline earth metals are the second group on the periodic table, so beryllium and down. And which group from number 7 which of these groups become -1 ions? And it's the halogens. Remember, all of these, they just have to gain 1 electron to get the same electron configuration as a noble gas. So they'll gain 1 electron. And remember, when you gain an electron, you become negative. So gaining 1 electron is going to be a -1, and that's the halogens. And then the elements that have 6 valence electrons, so that's anything in oxygen's group. So oxygen all the way down to Lv, so O all the way down. Those would have 6 valence electrons. Okay. Number 10 is kind of a trick question. It says, which sample has more particles or more molecules? 2.5 moles of CO2 or 2.5 moles of H2O. If you have the same number of moles, you have the same number of molecules for a compound. So they each have the same number of molecules. So 2.5 moles of carbon dioxide has the same number of CO2 molecules. 2.5 moles of water has the same number as water molecules. Now, it's not going to be, on this chemistry county-wide summative, but maybe moving forward, if they ask you which one has the most oxygen atoms, the answer would be this guy, because in 1 molecule of CO2, there's 2 oxygen atoms. But in 1 molecule of water, there's only 1 oxygen atom. So that would be maybe a way they could play the game. But right now, if I have 2 moles of this and 2 moles of that, that means I have the same number of particles of each thing. Okay. Explain how an atom of magnesium becomes a +2 ion. So remember, +2 means I lost 2 electrons. If we look at, magnesium's electron configuration, 3s2, that's its valence electrons. So it loses 2 electrons. And if you want to be specific, it loses 2 electrons from the 3s sublevel, because that's its valence shell. Okay. So this one, write the symbol notation for a particle that has 20 protons, 20 neutrons, and 18 electrons. So the first thing I would note is that the electrons and protons aren't the same, so that means there's a charge. If you have less electrons, it's a positive charge. If you have more electrons, it's a negative charge. And the symbol notation, remember, it's mass number here, atomic number here, chemical symbol. And if the protons and the electrons were the same, then you wouldn't write anything here because it would be neutral. But we write a 2+ here because we have 2 less electrons than protons. So the overall charge is +2. And then remember, to get the mass number, it's just protons plus neutrons. Don't go to the periodic table and round. It could be the answer, but it might be a different isotope. So 20 protons plus 20 neutrons, I have a mass of 40. Okay. So calculating average atomic mass, we need to know the mass number of each isotope. So here we got 30, 31, and 32. That's the mass of each isotope, mass number. And we need to know the percent abundance. So they give us the percent abundance for isotope 30 and isotope 31, but they didn't give us 32. But remember, all we would have to do is subtract from 100. So 32, so 25 plus 15 is 40. So the missing percentage is 60. So that means isotope 32 is 60% abundant. And then all we do is mass number times percent, mass number times percent, mass number times percent, and we add them all up. If you do it the way I do it, remember you have to turn your percentages into a decimal. So instead of 25.25, instead of 15.15, instead of 60.6. Now you could keep this as 60, you could keep this as 15, you could keep this as 25, but then at the end you'd have to divide by 100. Okay. And remember, the units for average atomic mass are AMU, atomic mass units. Okay. And just read the instructions and set it around to two decimal places. So that's my answer. Okay. Here we're given the symbol notation and we have to figure out protons, neutrons, and electrons. So the first thing I would note is there's no charge written here. So that means it's neutral. So that means protons and electrons are the same. Remember, atomic number is protons. But since it's neutral, that's also the number of electrons. So I know in this atom of fluorine, I got 9 protons, I got 9 electrons. And then to get the neutrons, you do mass number minus atomic number. So 21 minus 9, that's where we get the 12 from, 12 neutrons. Okay. So nuclear equations. One thing I just want to note real quick is on the checklist, the first thing on the checklist has some vocab stuff to kind of understand. So sometimes like the state of Virginia, the county, they'll use different words that mean the same thing that we're kind of used to using in chemistry. So all throughout unit 2, when we're doing nuclear, we called it nuclear decay. So, a fission reaction would be a decay reaction kind of idea. But they use disintegration on the test. So if you see disintegration, you kind of replace it with nuclear decay. If you see energy states, you could think energy levels. And then we've been using heat, okay, as a word for energy. They're using thermal energy. So if you see thermal energy, you can replace it with heat, that kind of thing. So those are so these are the words to look for on the county exam. And this is what they really mean to us: nuclear decay, energy levels, and heat. Okay, so whoops, incorrect button. Okay, so back to the key. So nuclear decay, beta decay of cobalt-60. So we would write cobalt-60 yields a beta particle, and then we do our math. So this number is 60. This number is 28 because 28 and a -1 equal 27. And then we get nickel because we go to our periodic table. Atomic number 28 is nickel. Okay, so that would be the equation for cobalt-60 undergoing beta decay. Here we have alpha decay. So instead of a beta particle being produced, we got an alpha particle being produced. And so it'd be thorium-232 yields an alpha particle. This number will be 228 because it would be 232 minus 4. This number would be 88, 90 minus 2. And then we get our chemical symbol. Atomic number 88 is radium, so Ra. Okay. Then here we have a half-life problem. They give us the half-life of carbon-14. So what does that mean? It means every 5,730 years, the sample cuts in half. And it's saying we're starting with a 100 milligram sample of carbon-14, and we want to know how much is going to be left after this much time. So the first thing to do is take the total time and divide it by the half-life. And remember, at this level of chemistry, that's always going to be a whole number. So that means the sample's going to cut in half 3 times. We're starting at 100, so we're just going to divide by 2 3 times. Okay, so 100 divided by 2 is 50. That divided by 2 is 25. And then one more half-life divided by 2 is 12.5. So after 3 half-lives, if we started with 100 milligrams, we should end up with 12.5 milligrams. Okay. Here, it's saying take these models of an atom and put them in kind of order in which came first in history. So just remember, the quantum model is our current model. So until we change that model, it's currently the quantum model. So solid sphere, that's kind of gets attributed to Dalton. Remember, Democritus, and then a lot later in history, Dalton's atomic theory. He said atoms were these small indivisible spheres. So solid sphere theory. Then we started to note that there are things smaller than an atom, so subatomic particles. And the first model after Dalton's atomic theory was J.J. Thomson and the plum pudding model. And then that was proven wrong by Rutherford. And then Niels Bohr and them came up kind of with the Bohr model, which is kind of like the planetary model where you think of, you got the nucleus in the middle with the electrons orbiting kind of like planets. But now we have the quantum model where we still use a lot of the vocab from the planet model, like energy level and that kind of thing, in orbital. But an orbital doesn't mean what it meant in the planetary model. But this would be the order from, earliest model of an atom to the most current model of an atom. Okay, here we have a heating curve, or in this case, a cooling curve. So remember how to interpret this, right? So up here would be from A to B, we're a gas cooling down. From B to C, we're condensing to a liquid. From C to D, we're a liquid cooling down. From D to E, it would be freezing. And then from E to F would be just a solid cooling down. So solid particles vibrating slower as we go from E to F. C to D would be liquid particles moving slower. A to B would be gaseous particles moving slower. And then remember, at the plateaus, we have the phase change. So if we're cooling it down, we have condensing going this way. We have freezing going this way. And if we reverse the direction, we have like solid particles vibrating faster, and then we would have melting, and then liquid particles moving faster, and then we would have vaporization or boiling, and then B to E or B to A would be gaseous particles moving faster. Okay. Another thing to remember is kinetic energy. Average kinetic energy is the same thing as temperature. So it's saying which line segments is kinetic energy decreasing? Well, the only time temperature is changing. So from A to B, we're decreasing in kinetic energy. From C to D, we're decreasing in kinetic energy. And from E to F, we're decreasing in kinetic energy. And then it says which line segments show intermolecular forces forming. Remember, during a phase change, if you're melting or vaporizing, you're breaking intermolecular forces. If you're freezing or you're condensing, those IMFs, those intermolecular forces, are turning back on. So from B to C, we're turning on intermolecular forces, and from D to E, we're turning on intermolecular forces. If we reversed it, if we were heating it up, E to D would be breaking intermolecular forces, C to B would be breaking the rest of the intermolecular forces that are holding the particles together in that state, okay? So F to E would be increasing in kinetic energy. D to C would be increasing in kinetic energy. B to A would be increasing in kinetic energy. Okay. But from C to B, kinetic energy is not changing. From D to E, E to D. Okay. And I know kinetic energy is not changing during that time because the temperature is the same, right? And remember, average kinetic energy is directly proportional to temperature. Okay. All right. I think that kind of covers it. Again, this is nothing to stress about, just kind of review. Make sure you go back and review a lot of your Unit 2 stuff. Remember your Avogadro's number calculations from Unit 1, and you're kind of all set. Okay. So shouldn't have any difficulties with us. All right. Keep it real.